So today we're going to talk about mass spectrometry, which is another one of the instrumentation techniques that we're going to look at. Unlike the others, this one is not looking at the way light interacts with our molecules. This is looking at electron bombardment and ionization and breaking the molecules. So let's have a look at it. So you may remember back in one of the first topics that we did when we talked about atomic structure, we looked at mass spectrometry and how it can be used to determine the relative atomic mass of atoms and their isotopes. And we had the formula for the relative atomic mass using isotopic mass and percentage abundance. We can extend this technique into using molecules, not just single atoms. So in this case, it is important for us to remember that we can see isotopic distribution with mass spectrometry, but one of the ways it's used primarily with organic molecules is looking for the way this technique interacts with molecules. So what happens is we have our molecule in the gaseous state, we fire an electron beam at it, this knocks out an electron from our molecule, creating a positive ion, and two electrons being generated as well. So this is the general equation for how the mass spectrometer works. So essentially the electrons come in, they knock out a second electron, creating a cation which will have an unpaired electron. So it's a radical cation, and we can use the radical notation to show these, but more often than not we tend to use the plus for the cation. So essentially mass spectrometry, we always have a gaseous sample and we have high energy electron beams to form positive ions. It's critical that we remember the positive ion part of it. One of the most common errors in exams is forgetting to show that the species responsible for the line or the signal that we see in the spectrum is actually a positive ion, and we need to identify that when we identify the fragments. So because this removes an electron, creating a positive ion, the cations are then accelerated by the electric field and deflected, as you may remember. And we saw this one back in our first year of study, in that we have liquid samples or solids, and they're vaporized when we inject them into the instrument. Then they're ionized by the electron beam. They're accelerated, deflected, and detected, remembering that it is the lightest atoms with the highest charge that are deflected the most. And then they are detected by a computer or a detection system attached to a computer, and we generate the spectrum from that. So this is just a schematic of the diagram. So we have vaporization, ionization, acceleration through charged plates, deflection through the magnetic field, and then the ion detector at the end is how we actually count the ions or see the ions that we're talking about. So just a key point to remember is that this does depend on the ratio of its mass to charge, which forms the x-axis on our spectrum that we see. It is unlikely when we are talking about molecules within the course that we study that you will see positive, multiply charged species. Possible, but unlikely. Okay, so generally the questions relating around instrumentation for the identification of organic molecules will be looking at singly charged species. So we use mass spectrometry in a qualitative way. We primarily want it to determine the molecular mass, so that if we're given percentage composition or an empirical formula, we can work out the exact molecular formula of what we're talking about. And we look at the molecular ion or the parent ion in order to identify that. We can use it for the to identify isotopes, and also to help in the identification of structure via the fragmentation pattern. So generally what we're talking about when we're talking about our spectrum is the peak with the highest mass to charge ratio, okay, which is essentially, if our charge is +1, going to be our mass, is due to the molecular ion or the parent ion. So the one that is highest up on the spectrum will be our parent ion. This is not always the largest peak. We can have much larger peaks in our spectrum, but the one that is the furthest to the right that has the highest value will be our parent ion. Then we see other peaks that create what we call a fragmentation pattern due to the molecule breaking up. So this can be due to different isotopes or fragmentation. So just another way of looking at our ionization. So we knock an electron out, we get left with a positive molecule. When we have, or atom, when we have molecules, what can happen is bits can break off. One part of it will be positive, the other part of it will not be positive. Okay, it will be uncharged. Now here's the thing, the machine only sees the positive ions. So if it breaks apart, the bit that we see is the positive ion, and then we can also work out what it lost. And the bit that was lost is not seen. We just see multiple fragments because of the large number of molecules that are breaking up. So if we look at a simple molecule of something like chlorine, this shows us both the isotopic distribution as well as the effect of the parent ion. So if we think Cl2 is a covalently bonded molecule with two chlorines, there are two isotopes of chlorine. There are chlorine 35 and chlorine 37. So if I have a chlorine molecule that has two chlorine 35s, then I will have a peak at 70. So this is essentially here something that we see when we have halogens, in that we get a isotopic pattern in our parent ion as well. So these three peaks at the top here actually represent the parent ion, but they're three different parents because we have the blue one here, which is two chlorine 35s, the green one, which is two chlorine 37s, and then this red one here, which is a chlorine 35 and a chlorine 37. So because we have very abundant different isotopes of chlorine, we can see this isotopic distribution around the parent ion. The other peaks that we see down here are, of course, this one at 35 is one chlorine molecule, one chlorine atom, chlorine 35, and one chlorine 37. Remembering that these, of course, would be the positively charged species of each one. Okay, so they're actually positively charged because the machine is seeing them. So when this bond breaks, we are seeing the consequence of that, and you'll notice that because more chlorine 35 would be present, because it has a higher relative abundance and is present in more of the combinations, we actually see more chlorine 35 in the spectrum here. So if we look at something like dichloromethane, again, because it contains chlorine, the CHCl2, we see an isotopic distribution of the peaks here due to the different chlorines. Okay, so this is a CH2Cl2 parent molecule here with a mass of 84, and then this is the one where we've got the chlorine 37 and chlorine 35 combinations. Then, of course, we have one here at 49, which is the loss of 35 AMU, and these cluster of peaks around here will be the other isotopes of chlorine as well. But primarily, we are looking for a parent ion and then any fragmentation that may give us an idea as to the structure of our molecule. The parent ion is the one that's highest on the spectrum. This is still a parent ion here, but again, remembering isotopic effects. And then the base peak is the most common fragment. So when the molecule breaks apart, it will break apart more often in a particular way, and the fragment that we get from that breaking will usually be our base peak. It is our most common fragment that we see. So if we look at ethanoic acid, remembering that ethanoic acid has two carbons, carboxylic acid, and then the CH3 group, we can see here that if this whole molecule is ionized, we get the parent ion at 60, because this would have 60 grams per mole as our molar mass. We will see peaks at 45, which would be the breaking off here, and the C double bond OH becoming ionized. We can also see a peak at 43. Which is our most common fragment, which is the CH3CO, which is actually the breaking through between the C double bond O and the OH, and also a CH3 fragment and a COH fragment, and then a CH2CO fragment here as well. Primarily, the parent ion in this one and the 45 would be the most diagnostic peaks because they inform us more about the structure of the molecule. And this is showing the fragmentation pattern here. So where we've lost C double bond OH, we have the molar mass of 15, or the atomic mass of 15. Loss of OH will give us the CH3CO, and you'll notice that each of these fragments that is responsible for the mass that we're talking about is shown with a positive charge, because the machine does not see them if they do not have that charge. So the mass spectrum is incredibly sensitive. It allows us to identify substances in very low concentrations. Over time, there's been large numbers of databanks created of mass spectra, and they allow analysts to detect the presence of that in a sample. So we can put in a sample, it can be run against these databases, and we can detect what those fragment patterns usually result from, and use it to detect the presence or absence of certain chemicals. The machine itself is actually sensitive down to about 10 to the negative 9 grams being able to be detected. So it's really good for low levels of pollutants in the environment, and also for the analysis of air spectra, to look at the composition of pollutants in our air, which we can detect at very low levels. Mass spectrometry is used widely in a number of industries, including looking at pharmaceutical samples, medical screening for particular metabolites in the blood, perhaps, that we're looking at, for drug testing, environmental samples, and geological samples. So looking for trace elements of oil and gas that might be present in rocks that people would be interested in mining or using. So if we have a look at this problem, we'll do a couple of samples and then we'll wrap up this video. So this is a mass spectrum for pentane. So if we think about this, 1, 2, 3, 4, 5, with hydrogens in each of these places. Okay, if we have a look at this, this is going to be our parent ion here because it's the furthest to the right. 72, and that makes sense because we have 1, 2, 3, 4, 5, which is 60, and then 12 hydrogens, that gives us a 72, so that is consistent. The base peak is going to be this one here at 43, and then we can see we also have labeled peaks at 29 and 57. In a problem, the first thing I would go to is the labeled peaks. Don't try and look for things outside of those unless you think it's really necessary. So when we look at this, we can look at the semi-structural formula of pentane, and as we said, it would have a molar mass of 72 grams per mole, which would match the 72 peak at the mass to charge ratio. And we can assume that it is given by this ion here. We put it inside square brackets, which is the whole molecule, and then give it the plus to show that we know that it would be a positive ion. Then we can look at the fragments. We can look at what fragments we would expect, or we can look at the fragments and justify them. It is a bit of trial and error using the table from your data booklet, okay? And for exam questions within what we're looking at, don't try too far and look for the ones that aren't listed. You just want to find ones that are diagnostic and help to support your argument. Okay, so we would expect to see a methyl group because we're looking at a standard hydrocarbon that would have methyls on each end, and would give us 15 AMU. And we can see here that if we take 72 minus 15, we would expect to see a peak at 57 as well, which we in fact did see in our spectrum here. Okay, so then we can also write the corresponding fragment for that. So for 57, we would have our parent molecule minus a CH3 inside the square brackets with the positive ion. So then when we have larger fragments, we need to think about what's happening. Okay, so we could have been left with CH3, CH2, CH2, losing a CH2, CH3, which would give us 43 AMU, and we do in fact see that peak in our spectrum. So it's a matter of looking at the molecule and thinking about what you might have lost, and then seeing if there is a peak in the spectrum that corresponds to what was left over. So when we look at the final spectrum and things that we've considered in terms of our structure, we can see that we have the parent ion at 72. Then we have a loss of a CH3 group at 57, and the loss of a CH3, CH2 we've also lost for the 43. So from this, it's consistent with the idea that we have a straight chain alkane, and the peaks that we're seeing are due to fragmentation, due to loss of CH3 or CH2 groups and their combinations. Again, these are the fragments that you are given in your data booklet. You can use these to help justify. They won't all be in there, so if you are simply looking for like a CH2, CH3, the 29 is there, but you might see a CH3, CH2, CH2 if that is more consistent with the molecule that you're looking at. So remember, this isn't about precision, this is about finding the things that match what you suspect and using that to support your answers in terms of the molecules. We've talked about detection of isomers, and we looked at the initial problems which showed us that we can see isomeric patterns in our spectrum. So if things look a little bit weird and you've identified what you think would be the parent ion, but there's a couple of smaller peaks that are around it, they're possibly due to ions. So consider that when thinking about your solution. Okay, so let's have a look at this and think about two isomers of pentane and which fragments would allow you to distinguish between them in a mass spectrum. So see if you can come up with two and a justification. Pause the video and then come back. Okay, so if we have a look at this, here's another worked example for us. Hopefully you were able to justify your pentane, and we'll have a look at that the next time we meet in class. But let's look at this one. We have CH2O and we have a mass spectrum for it, and we're given that it has a parent ion here of 60. If we think about this, this is going to be 12, 14, 30, which means that our molecular formula must be 2 times that to get to 60. So it would be C2H4O2. Okay, so now we can start to see we have a peak at 45. I'm going to be thinking straight away C double bond O, OH. 43 is now going to be a loss of 17, which could be the loss of an OH. So that would leave me with C2H3O. And then, of course, this one here screams I'm a CH3. Okay, and of course, these are our positive ions here. Okay, and this is going to be our parent ion. So putting all that together, we have the molecular formula. We have a CH3 plus, a CH2, a C2H3O plus, and a COOH. So if we try and put that together, of course, we will get what we looked at earlier, which is ethanoic acid. And we can use other forms of spectroscopy like the IR to help support that. So we would expect to see that large, broad absorbance that we've been describing as a beard at around 3000. We would see a peak at around 1700 for the carbonyl. And of course, we'd see the CH stretches up around 3000 as well, which would help to confirm that this was in fact ethanoic acid. These are the questions from your textbook that you should work on. And then hopefully this has started to make a little bit more sense, and we're getting much better with identifying what's going on in our spectrum.